Imagine a giant mirror blossoming in orbit over the blue curve of the Earth, almost like an invisible flower. A wafer-thin film gently unfolds from its creases. Its metallic surface delicately sends the light it steals from the sun back, casting a soft, moon-like white glow through the clouds onto the ground. When you first hear it, it might sound like a science fiction scene, but this scene is real. This is the story of one of the most unusual apparatuses humanity has ever sent into space, a space mirror. Two separate attempts, a brave engineer, and finally, the silent but definitive verdict of physics. The idea of collecting and directing light is not new. One of the enduring legends of antiquity tells of Archimedes igniting Roman ships with burning mirrors during the siege of Syracuse. Historians debate the likelihood of this story. However, the power of the legend shows how far back the human desire to tame light goes. Centuries later, at the dawn of the rocket age, the pioneer Hermann Oberth envisioned a giant concave mirror in orbit. The goal was to direct sunlight to a specific spot, perhaps to heat it, perhaps to illuminate it. The drawings on paper, when tested by the harsh language of physics, turned into a different picture. Light reflected from orbit does not focus like a lens, it only changes direction. Thus, what forms on the ground is not a small, hot needle point, but a wide, soft patch of light. In the wartime atmosphere of the 20th century, this dream also became material for exaggerated weapon designs. Concepts like the sun gun produced schematics claiming one could scorch a city with a giant reflector. But the reality is this: light reflected from the high altitudes of space spreads out when it encounters the atmosphere. It creates a dim circle instead of a small focal point. Therefore, there is no death ray, but an artificial full moon is possible. And this is precisely where an engineer who chased after this dim but intriguing possibility steps onto the stage. Vladimir Sironyatnikov was one of the brightest space engineers of the Cold War years. We know him as the architect of the famous APAS, Androgynous Peripheral Attach System, docking mechanism that made the rendezvous of the Soviet Soyuz capsule and the American Apollo spacecraft possible. His signature is at the heart of the connection philosophy used safely for years on the Mir space station and later on the International Space Station. But Sironyatnikov had another dream preying on his mind: solar sails. The idea was to utilize the momentum of photons by deploying large reflective surfaces, accelerating slowly but with persistent patience into deep space without consuming fuel. The theory was beautiful. The cost to practice seemed unattainable in the early 1990s as the Soviet Union was collapsing. The spirit of the time demanded usefulness here and now, rather than romantic distant horizons. At this very point, Sironyatnikov pivoted his idea. He would use the mirror not as a sail, but as a reflector, casting a soft light from space onto northern cities where the night lasted longest. Near the Arctic Circle, the sun does not rise for days in winter. It's difficult to unload cargo at ports, keep construction sites running, or operate open-pit mines. Energy consumption for lighting and heating increases exponentially. What if it were possible to cast a full moon-like brightness from orbit onto the desired region at the desired time? Perhaps safer shifts under the shadow of port cranes, or clearer visibility on ice roads. Or perhaps a few minutes of wide illumination during critical moments like search and rescue operations. The project was given a name that means banner or flag in Russian, Znamya. The roadmap was like a folding schematic. First, a small demonstration, followed by larger-scale versions, and finally, a chain of mirrors. Each satellite would unfold a disk made of ultra-thin metallized film by spinning it in orbit. It would reflect the light it received from the sun onto a specific target. In theory, if multiple satellites aimed at the same target, the brightness could be increased. They could even open daylight windows over the night along certain lines. Of course, everything is clear on paper. The truth lies in the details. The plan for Znamya 2 was simple but full of subtleties. The reflective surface was compressed into a 40-kilogram drum folded like 8 petals. This drum was to be attached to the nose section of the uncrewed Progress resupply vehicle heading to Mir. After the vehicle separated from the station, the drum would start spinning with an electric motor. The centrifugal effect would unfold the petals, forming a circular disc. While the disc spun on its axis, the small thrusters of the Progress would both aim at the target and keep the surface at the correct angle. The orbit, the solar angle, and the location of the target on Earth would be calculated moment by moment, attempting to keep the patch of light as steady as possible on the ground. On October 27, 1992, Znamya 2 launched. Progress docked with Mir. The crew installed the drum carrying the folded reflector. Checks were completed. The vehicle separated from the station, drifted about 150 meters away, and the drum began to spin. The thin film unfolded like a lotus leaf. The surface captured the sun. On the morning of February 4, 1993, an extraordinary phenomenon occurred over the skies of Europe. A circle of light approximately 5 kilometers wide, starting from southern France and extending to Western Europe, swept across the Earth at the speed of 8 kilometers per second. The brightness was roughly at the level of the full moon. Where the clouds parted, this glimmer was seen for a few seconds. Most observers did not even look up that morning. As soon as the experiment ended, the mirror was deliberately deorbited and burned up in the atmosphere, leaving a faint trail over Canada. It wasn't a headline-grabbing show, but for the first time in history, a deliberate mirror light from orbit had been cast upon the Earth. This small, clean success opened the door to a more ambitious step. Znamya 2.5 aimed to increase the diameter to 25 meters, deploy the material more smoothly, and stabilize the patch of light over the target for a few minutes. The flight began on February 5, 1999. The initial moments passed calmly, but at a critical point of deployment, the ultra-thin film snagged on an antenna of the Progress. The tensioned material tore. Ground control attempted small maneuvers with the thrusters. They changed the spin rate. They played with the control parameters, but the asymmetry created by the tear could not be fixed. The disc became unstable. The attempt to lock onto the target failed. The mission was aborted. The mirror burned up in the atmosphere. A single fragile failure was enough to slow the pulse of an entire program. Znamya 3 was never built. The question of why forms the most instructive part of this story. Physics speaks clearly here. When you focus sunlight on a leaf with a magnifying glass, the focal length is measured in centimeters. A wide flux is compressed into a millimeter-sized point, and the heat instantly rises. In an orbiting mirror, however, focus loses its meaning. Light only changes direction and reaches the ground, drawing a wide distribution. What emerges is never a lightsaber, but an easy-on-the-eye brightness similar to the full moon. This brightness has practical utility, but claims such as turning a city into daytime or significantly reducing the heating load do not approach reality in most circumstances. The language of engineering is even sterner. Folding structures unfold in space, an environment free of gravity but full of thermal stresses. The material's thickness, on the order of microns, can turn even a millimeter-sized crease into a major deviation. A tiny tear on a spinning disk makes the entire surface asymmetric. The control system constantly expends thrust to counteract the imbalance. Fuel consumption increases. Pointing accuracy decreases. Add to this the differential thermal expansion. The surface facing the sun heats up, while the part in shadow cools down.
In engineering, good enough often beats cooler ideas, because the sum of cost, risk, and maintenance burden has the final say. The environmental and biological repercussions of Znamya were also worth debating. The human body's biological clock is set by darkness. Many processes, from melatonin secretion to sleep quality, mood, and immune rhythm, are synchronized with the night. While it is known that the light pollution of cities affects bird migrations, insect populations, and the navigation of sea turtles, predicting the long-term consequences of an artificial full moon chain deployed from orbit is not easy. Znamya's light was gentle. But even gentle light, in the wrong place and at the wrong time, can make unexpected touches on the delicate balances of nature. Despite this, the Znamya experiment is an honest turning point of the kind technology history favors. It is a practical answer to the question, can we do it? The answer is partly and briefly. This is not a disappointment. It is an opportunity to understand reality. Because sometimes the value of an idea lies not in changing the world, but in showing us our limitations. Znamya left invaluable lessons on how deployable membrane technologies, precise attitude control, and low-mass structures work in space. It provided genuine answers to the questions of what works and where we struggle in many fields, from solar sail research to inflatable structure designs, from origami-based folding schematics to thermal balancing coatings. If it were attempted again with today's tools, better materials and smarter control software would likely be used. Ring trusses to keep the surface taut, multi-layer membranes to reduce creasing, high-precision inertial measurement units supported by star trackers, vibration-free attitude control with micro-thrusters, perhaps even a swarm of small mirrors instead of one giant disk. It would be possible to increase the brightness on the ground by overlapping the light, but the fundamental reality would still be the same. The light falling to the ground would still be a wide and gentle illumination. Physics is poetic, but not open to negotiation. Let us also look at it from the window of astronomy. The dark sky is not just a romantic backdrop. It is necessary for us to discern the universe's faintest details. Wide-area artificial light patches can create interference in sensitive measurements. Short and infrequent passes, like Znamya's, can be managed with planned warnings. But a long-term schedule of a mirror chain would require more intense coordination with observational astronomy. The sky is the common area of science as much as of technology. Every step taken here requires a multi-stakeholder balance. When we come to the cultural echo, we see that Znamya's brief glimmer has a long shadow. It found a small scene, a side story, a symbol in popular writings, documentaries, and novels. Human imagination transforms even a fleeting play of light into a long narrative. That soft illumination falling over a square was also a symbol of our relationship with technology. A hand reaching for the sky not to abolish the night, but to understand it a little better. Perhaps that is why even the failure itself is remembered with tenderness, because you say, they tried. It didn't work, but it taught us a lot. Now let's rewind the camera to that morning. A gentle whiteness streams for a moment over the bare winter trees in southern France. A farmer shields his eyes with his hand and looks up. Passengers waiting on a station platform are briefly drawn by a flicker. A driver on a snow-laden mountain road sees a ghostly halo of light beyond the headlights. The illumination slides eastward toward the white peaks of the Alps within seconds, then to the plains, and from there to the distant horizon. The earth turns, the mirror fades. The story, however, is etched into memory. And as we gently close the story, we can say this. Znamya was not just an engineering experiment. It was a venerable recollection of curiosity and attempt. It burned no one, it scorched no city. It merely left a brief signature in the sky and quietly withdrew. That signature was a small sign illuminating the march of science on the fine line between the possible and the imagined. Perhaps one day other mirrors will unfold, perhaps for entirely different purposes on entirely different routes. But every attempt will make us a little wiser, because every attempt offers a small opportunity to understand the world and ourselves better. We borrow the light, and we give it back. We carry the curiosity. Perhaps that is the truest part.